This is Kettering University.
Thank you. Thanks for the nice introduction, and nice to know it wasn't just lunch that drew the A students here today and faculty. Today I'd like to talk to you a little bit about the challenges of using the new class of steels in automotive applications. The presentation, this is very sensitive here, we'll talk a little bit about the automotive market trends, the new steels, demand for the new steel grades, a review of our future steel vehicle program, and then the question is, can we deliver the steels that are necessary to help the auto guys meet their lightweighting challenges? If you're not familiar, these are a couple cars you should be familiar with. The first car that was introduced, and then where it's evolved to, and we show the battery electric vehicle here to help meet some of the challenges in today's automotive world. Wanted to talk a little bit about the evolution of steels and the evolution of the vehicle, but more importantly, I guess wanted to point out the headline from Cars magazine about the fact that the day of the passenger car made primarily of iron and steel is on the wane, giving ground to aluminum, magnesium, and plastics. You can see that that was published in October of 1953. I'm here to tell you that the rumors of my demise are greatly exaggerated. Cars magazine doesn't exist, but steel is still the material of choice for automotive applications. I wanted to show you some of the vehicles that have been introduced recently and the structure behind the vehicle body panels. And you can see it is very heavily steel. Each color is a different type of steel. So the challenges in today's world is, can we meet the individual functions of each of those automotive structural components with the steels that are available, and at the same time meet some of the other challenges that the auto makers have. A little bit about North American vehicle production. 2009 and 10 are behind us. Yay! And the things that's leading the United States out of the Great Recession is really the automotive industry. Commercial construction isn't, residential construction isn't, industrial production is not. Automotive is leading the United States out of the Great Recession. It has grown very well. Automotive production is still forecast to grow up to 18 million by 2018. And the North American automotive industry is one of the most competitive in the at this time. What's driving the design of your vehicle? This is the evolution in automotive. Back in the 80s, what were the key design considerations included cost, styling, and corrosion. Everybody, well, I'm sorry, maybe most of you do not remember the cars of the 70s and 80s that had a tendency to rust, and you could, on missing your brake, actually put your foot through the floor because of the rust there. But the steel industry provided the solutions. We've got IF steels to make very complex parts and zinc-coated steels to help provide the corrosion resistance required of the automotive industry. In the 90s, crash became more important and people more aware of crash requirements and safety requirements. And that's where we started to introduce the high-strength low-alloy steels, and I'll talk a little bit about those later. In the 2000s, fuel economy became more of an issue. Cost as always, and more crash requirements, and I'll show you the evolution of crash on the next slide. And then the 2020s, we know that we're going not from where we're at now, but we're going to 54.5 miles per gallon requirements in 2025, and I'll show those in a minute too. But this I'll show both of you, if you look real quick. This is the evolution of the crash requirements, and it's both regulatory and customer driven, right? The government tells us through FMVSS and NCAP what crash requirements are required as far as intrusion, door intrusion, as far as frontal crash requirements, rear crash requirements, rollover requirements. But more importantly, the customers are demanding it too. And that's really what's shown with the IIHS test, the Insurance Institute for Highway Safety. They're the ones that actually have to pay out for damage on the vehicle, or death in a vehicle, or serious accidents in a vehicle. And they have a lot of data that tells what happens on vehicle crashes. So they're the ones that actually in 2012 introduced the 25% narrow offset. That's where just the quarter of your car hits the quarter of the oncoming car. And that's very severe for both the vehicle and the passengers. In fact, we'll show a couple videos recently. If you see that oncoming car and that front crash happening, because of how it's designed with the structure, it might be best to choose to hit them front on versus hit them at 25% offset. Also, what's really become important now is meeting the new CAFE requirements, the new EPA and NHTSA requirements as far as fuel efficiency. You can see we're going from the current levels that started with the initial CAFE laws back in the 70s and 80s when we had the oil embargo and the problems associated with getting oil, to where we sat for many years on the fixed mile per gallon period, where actually performance ruled, right? And infotainment ruled, and more content for your vehicle, but better performance for your vehicle. Who can get 0 to 60 faster? Who can put more of an engine into your vehicle? We were meeting those challenges during that long 30-year time frame, but over the next 15 years, we've got to go from our current 27 miles per gallon on average up to 54.5 miles per gallon. And what's the challenge in doing that? They always have to address that with a little bit of everything to meet those challenges. What's happening in general to the automotive market? These are some of the drivers. It's an international market, so you've got to worry about the earthquakes and tsunamis in Japan, and the flooding in Thailand, and the plastic production in Germany. That's, it's global and some are single sourced. I have a friend who couldn't get a backup video camera in his VW Touareg because the plant in Japan was affected by the tsunami. So you've got to worry about the global marketplace. You've got to, of course, always worry about oil and gas. There's a lot of pent-up demand, and I'll show you a little bit of that in a minute too. And then government regulations, and we talked about that. And what's driving each of those? We see government regulations right now, they're set, right? We know what the crash requirements are, we know what the fuel efficiency is, so we might have a general feel if it's good or bad news for steel, but for auto, they know where it's set, so they are on a pretty even keel. Material cost, OEMs are announcing price increases to absorb commodity costs. That was when this was put together. Right now, though, material costs are pretty well set. As I said, there's not a lot that's helping drive the economy out of the Great Recession, but auto is. So we want to make sure we continue to meet the automotive requirements. Globalization, energy costs. So there's all things that we look at when we start to work with our automotive customers to make sure they have the steels of the futures and they can build the vehicles that they're building. I talked a little bit about the vehicle itself and the performance of your vehicle. You can see here the chart that says over the years, and we've tracked this now for about 10 years, what's the amount of steel in a vehicle? And that's very important for us because my job is to make sure that steel remains a material of choice and we grow the amount of value-added steel, these advanced high-strength steels. So you can see on a 5-year average, we're looking at about 62% of the vehicle is made of steel. And we are charged with keeping it that way. Actually, we've got a goal with our board of directors at maintaining a 57% content level, so we've got something to shoot for over the next 3 to 5 years. I talked a little bit about the average age of the vehicle and the population and the pent-up demand of the vehicles, and this is a pretty good chart that shows you how good vehicles are getting nowadays. That you're buying, probably a lot of you in here have vehicles that are 7, 10, 15 years old. You've still got a pretty good vehicle. If you look here, the average age of the vehicle population, and there's about 250 million vehicles on the road in the United States right now. Average age is up at about 11 and a half years. We think there's a lot of people that would like to change that and start putting younger vehicles on the road, buying new vehicles. That's why we consider this a very large pent-up demand for vehicles. We also, in our discussions about vehicle content, material content, I mentioned the fact that I've got to grow these advanced high-strength steels. And this is a chart that was developed by Ducker, an independent third party, that says the amount of advanced high-strength steel is going to be growing at a pretty steady rate. And in fact, when this was done back in 10, 11, they said advanced high-strength steels are the fastest growing lightweighting material used for automotive applications. Growing faster than aluminum, magnesium, and plastics. And that was done in 2011, and maybe things will be changing because we've all heard the news, but wanted to give you an example. Again, you saw those pictures at the beginning of where some of these advanced high-strength steels are being used. Every year we have a seminar called Great Designs in Steel, and the Detroit 3 and international OEMs come in and give us a presentation on where they're using these advanced high-strength steels and the fact that they are growing their use of them to help meet safety and fuel efficiency requirements. So this is the 2014 Chevy Silverado, and you can see where they're using the advanced high-strength steels. And what they anticipate for the continued growth of the steels, they see the medium and mild steels are becoming less and less of their portfolio of material, where the advanced high-strength steels, the dual phase and the Martensite, are growing in usage at General Motors. We had a presentation by Ford on the Ford Escape, and you can see the portfolio of materials that they're using on the Ford Escape. You can see where each of those are used. At this time, it'd be nice to understand that in the front and the rear, they're using a dual phase steel because steel has a characteristic of getting stronger the faster you hit it. And there's a lot of room at the front and rear of the vehicle to absorb and manage the crash energy. So the crumple zones in front and rear are using the steels. We can really lighten them up because of the fact that we have that space, and dual phase and trip steels really increase in strength as you hit it. However, on the side structure, you don't have as much room to let a vehicle in. So if you get hit in the side, you want your vehicle to be strong enough to withstand that hit and push you out of the way before the vehicle comes in. And that's where the martensitic and the boron grades are used, because they can absorb that. They can manage the crash energy to go up the roof rail or maybe down into the floor and avoid you as the passenger. So you can see that on the Ford Escape, and then you can see it here on the Hyundai Sonata too. The side structure has the very high, ultra high strength steels, the martensitic and the press hardened boron steels. What are advanced high strength steels? They're alloys having chemical compositions like the high strength low alloy steels. You make that by the chemistry as well as the microstructure, but here you develop your microstructures thermomechanically by how you process it through your steel mill. And I think I've got a picture of some of the processing lines. I know I do have microstructures, so we'll just talk a little bit about metallurgy in a minute. So the advanced high-strength steels help the design engineers meet safety requirements, meet environmental emissions, meet your fuel efficiency by weight reduction, improve your durability, your fatigue, so you can continue to buy these cars and make them last 12 years. We also, again, looked at now and in the future where different steels are. This was done by Ducker, and you can see there is some growth in the aluminum and magnesium, but more importantly, very large growth in the application of advanced high-strength steels. And then this is our famous banana chart where we look at the material on the left is very formable. That's the IFs, like I talked about in the 1980s, provided you with the ability to form it. But as we've grown to the high-strength low alloys and to the martensitic, we get very strong, but not as formable. But these advanced high-strength steels, the dual phase, are aiming up for that upper right-hand corner to help with formability and strength. And we've got some research being done with EPA and the Detroit 3 and the North American Steel Industries on that peach-colored circle, which would be the third generation of advanced high-strength steels. This defines in more detail what the individual steel types are. And I guess I do want to point out that each of you, I hope, got your USB stick that has this presentation, so it'll help when I zip through it to meet the goal of a little after 1. But for your metallurgy lesson, again, the steels themselves, this is what they look like on a microstructural level. It's a composite of ferrite, austenite, and martensite. The mechanical properties have advantages for automotive applications. You want them to be formable, but you want them to be strong, so as you form them, you want them to convert to something that's strong. So high-strength low alloys were done and produced by grain refinement, precipitation hardening, and solid solution hardening. Dual phase is a dispersion of a second phase, a very hard phase, within a soft ductile ferrite matrix, so the ferrite can be formable, but when you form it, then that strong martensitic microstructure helps give you the strength. And the trip steels, or transformation-induced plasticity, introduced the austenite, and austenite is a very unstable microconstituent. So as you form it and add strain to the microstructure, that austenite transforms or trips into martensite. So it's formable as austenite, but when it trips into martensite, it's very strong, so it gives you the best of both worlds. And then this is more micro structures of the ferrite, which is a very stable microstructure. That's what steel would like to be, very formable, very stable. Martensite is when you quickly cool through the phases, you'll get that structure, and then you have to heat, cool again to get some of the dual phase and trip microstructures. So you need a basic understanding of the chemical, physical, and mechanical metallurgy of the iron-carbon system, so we'll talk about that in a minute, to help differentiate among the grades of these advanced high-strength steels. So in your stick is some reference material if you want to dive deeper into the metallurgy of these advanced high-strength steels. You can do that, and it is very interesting to read, and will keep you up late at night, I'm sure. The iron-carbon phase diagram, that's where I spent about 2 years of my college education, because back then we were metallurgists, and metallurgy was all about the phase diagram. And if you haven't had the chance, This is steel, and it is got years and years and years of research done in iron-carbon phase diagrams. This is just the two-dimensional. As you start to introduce more alloying elements, you can get to the three-dimensional iron-carbon manganese diagram or silicon or aluminum diagram. But this, what's important is you can see that from the liquid phase up in the upper left, the transformation of steel goes through 1, 2, 3, 4, 5, 6 different phases as it cools down. It goes from austenite, which is a face-centered cubic, to maybe a ferrite body-centered cubic, a pearlite where some of the iron or the carbon comes out. So it's a very complex system as it cools from the liquid phase. The work we're doing with EPA and the Detroit 3 really was predicated on some of the work they did on aluminum, which is an easy system, right? It's the integrated computational mechanical or metallurgical materials engineering. They thought they could take the learnings from aluminum, which is a single phase material, into steel, which has multiple phases as it cools down. And it's becoming a little harder than they originally thought. So this is austenite. This is what austenite plus ferrite as we're starting to cool from point to point. As it goes from the austenite region, it now forms the pearlite transformation. And that's what the pearlite ferrite looks like when it's pretty stable. And I didn't show you a martensite. We showed that earlier, which would be a rapid cooling through all the phases, so you don't have enough time to transform during each individual phase in the phase diagram. What's that do for you? I talked about the fact that you get some great properties with steel. So you can see it's very formable. The trip steels, the dual phase, and the high strength low alloy are very formable. If you put the strain in it, you can see that it goes a very long time, up to 20, 25, 30% without ultimate fracture. And that's what the OEMs, the Detroit and international OEMs really enjoy. And then I talked about strain rate hardening, which is unique to steel, is that it gets stronger the faster you deform it. So again, in the crash energy management, as you crash it, it slows down the energy of the vehicle that's hitting you because the steel is getting stronger as it is deformed. Talked about that. There are new strengthening mechanisms that are being looked at. We talked about third generation steels. So steels are not your grandfather's steels. In fact, the steels that are used today weren't used 10 years ago. So steel continuously evolves, and we are very successful in eliminating old steels with these new steels. Some of the things that are being looked at now are nano steels. Use a very fine precipitants to give you the very high strength and very high formability that's needed for the vehicles of the future to help meet the lightweight push that we have from our OEM customers. So you can see that you'll go from elongation hole expansion, which is a test that you put a ram through a hole and it expands, and we're very concerned with cracking along the edge of the hole. But with these nanoparticles, they feel you can get very high hole expansion, so you can make those intricate forms without fracture. And that's happening in research and development now. Wanted to talk a little bit about the ultralight steel auto body work and the Future Steel Vehicle program. It's an international consortia. Future Steel Vehicle was just completed in 2011 by 17 international steel companies that provide about 80% of all the automotive steels in the world. Some of the key findings was the fact that we developed a state-of-the-art computational or computer operating systems where they could then design these steels to meet the requirements of the vehicle. And if you look at the vehicle, that's where crash energy management happens. That's what's important. That structure is what your vehicle should look like if you didn't have to keep rain out of it. But to meet the safety requirements of the vehicle, that's what your vehicle could look at and meet all the crash requirements. This shows, potentially, some of the work that's been done on these steels and the fact that you can get weight reduction by going from a 1.6 high-strength low alloy. You have to remember how far it deformed because I've made it disappear, to the dual phase 600, that's a 6% weight reduction and deforms just as much, to the dual phase 580 with a 24% weight reduction. The other thing that's important about the Future Steel Vehicle program is that we offered up a solution to the OEs that offered a 39% weight savings from the structure of a typical vehicle. So we had a typical reference vehicle, and the Future Steel Vehicle provided a 39% weight savings. You ask what that reference vehicle might be, and unfortunately it's not one of maybe even the cars you drive, because it's a 98 Taurus size vehicle, but that is recognized through the industry because that's what was used in the PNGV program by the government to measure the challenge that they offered as far as weight savings and fuel efficiency improvements. So that's what the aluminum industry uses. That's what we use as a reference vehicle. The ULSAB program, you can see, offered weight savings. However, the Future Steel Vehicle program offers more. We're at about 35 to 39%. And you can see the peach or the orange intersects the pink. So we think that we are competitive with aluminum structured vehicles. Another of the key findings was the fact that we used the right steel for the right application in the body structure of the vehicle. So where you could absorb energy, we offered steels that could absorb the energy. Where you needed to take the hit and disperse energy, that's what we did. So we did that with 97% high strength and advanced high strength steels. And in fact, half that structure had over 1,000 megapascals or a gigapascal or greater as far as the strength of the steel. This is a chart that shows the evolution of steel. So when we go into an OE, we have a portfolio that they can work with of over 40 different types of steels depending on their manufacturing process to help them meet their requirements. And we also had 19 different advanced manufacturing technologies that they could use to meet the requirement of the individual component that helped us meet that 39% weight savings while still meeting the safety requirements. So we enable a 5-star crash rating, and that's always important. Now, we'll show you a crash of a 1959 vehicle to a 2009 vehicle. And this is one of the, great videos if you are into crash management and steel and stuff like that, but a terrible thing to do to a 1959 Bel Air. But you can see, and I'd like to say it's all steel that helps the people in the 2009 Malibu survive. But there is a lot that has evolved over the years as far as safety. There's seat belts, there's airbags, there's where the driver of the Bel Air didn't have any of those kind of requirements, and didn't have the windshield that absorbs crashes too, and just spider webs versus crashes and splinters and sends glass shards throughout the vehicle. So you can see why the Malibu person survived. Then another crash for the side impact requirements. You can see that it's very important to manage that. And back in 2003 is when the things start to evolve as far as absorbing the crashes on a side impact. And then the people started introducing the side curtain airbags. We are doing a lot in steel to help manage these crashes and even absorb the crash of a passenger car to an SUV hitting a passenger car on the side, which is very, very severe. The other thing that the FSV did was reduce life cycle emissions. There's more to fuel efficiency or the carbon footprint of a vehicle than the time they're on the road. And we did a lot to show that we could be very fuel efficient and meet the total life cycle or total carbon footprint reduction that you'd think would be better for the entire environment than just what you push out into the vehicle from the vehicle use phase. And you can see steel production is about 5 times less polluting than aluminum, 10 times less than carbon fiber, and up to maybe 20 to 25 times less than magnesium. The other thing that we did with the Future Steel vehicle is do all that at no cost penalty to the OEs. So their manufacturing costs, even though the steel on a per pound basis is more, but they're using less of it, so overall we save them money or didn't impact them. And the other thing is we've introduced more to the Future Steel vehicle where they can apply it now. They can start to use it now and take advantage of it. And that's what steel has done a lot of, is evolutionary changes, evolutionary weight changes. If we help you save 3 to 4% a year for 10 years versus something that promises 20% weight savings and doesn't deliver because of the manufacturing restrictions, we think we come out ahead. So it's an evolutionary weight savings that we offer. We work very closely in the Auto Steel Partnership with the Detroit 3 and the North American Steel Industries. This partnership has been in cooperative research since 1987. We've had some very good successes with different subsystems of the vehicle showing up to 30% weight savings on subsystems with the application of these advanced high-strength steels. And we have projects continuing on over, I think, 14 different projects at the Auto Steel Partnership to continue to work collaboratively. That's who I am. That's available on your stick if you've got any questions. Now's the time. Plus, if you've got any questions, you can contact me later.
Before we open up for questions, I just have a small gift for our speaker. Let's hear it for Mr. David Anderson.
Thank you.